Let me share the content. Right, can you see the slides? Okay. So recap everything before we move on. In the last lecture, we have discussed about two types of diffusion process. So which can be either constant source diffusion or the second one is limited source diffusion, right? Constant source diffusion or limited source diffusion. So the difference between the two types of this process is constant source diffusion. Your process has constant supply of phosphorus or boron throughout the process. Whereas if you talk about limited source diffusion, you're going to have your source for a limited time. For example, if you talk about constant source, if you are diffusing your emitter, for example, or your channel for 1 hour, and then for constant source, that means you're going to have your phosphorus coming into the furnace for the whole 1 hour duration. Whereas for limited source diffusion, you may have around 15-20 minutes or up to 30 minutes, for example, of phosphorus coming into the furnace, and the rest of the process, there's no new phosphorus supply to the wafers. So that's the difference. And if you talk about these two types of processes, they are associated with different diffusion profile or emitter profile. So if you talk about constant source diffusion, so you will have profiles like the one you see on the page right now. So going longer throughout the process or increasing the value of your DT, diffusivity times process duration, you're going to have your profile moving into the silicon or going into the silicon, but without changing the value of your N naught throughout the process. So you will see your N naught stay constant throughout the process, even though you vary your process duration or indirectly increasing your DT value. On the other hand, if you look at the limited source diffusion, or we call it Gaussian profile, the first one was called error function profile. If you increase your process duration or your DT value increases, diffusivity time process duration, you're going to see your profile moving into the silicon just like what you saw in the previous case. But in this case, your N naught value decreases as your DT value increases. So you're going to see your N naught value on the y-axis reduces with increasing value of your DT or longer process duration. And this is given by a Gaussian profile. So if you talk about error function profile and Gaussian profile, so they are different sets of equations that you need to use in order to do the calculations associated with these diffusion processes. So you can see both profiles as on this page. That's what you can see on this page. So the Gaussian profile is given by the one on the right, and the error function profile is given by the one on the left. So you will need to use this curve when doing calculation for either a constant diffusion process or limited source diffusion process later on. So before we move on into the calculation and the details of each, so let's go through this page on diffusion coefficient. So on our previous class, we discussed about some dopants or some impurities are substitutional in nature and some other impurities are interstitial in nature. So the way they are incorporated into the silicon lattice are different. So for example, if you look at the left hand side, the left side of the page, to the left graph, right? So you can see substitutional diffusers, which are common for a diffusion process like boron, phosphorus, aluminium, gallium, indium, and antimony. So you can see the diffusivity or diffusion coefficient values on the y-axis against temperature on the x-axis. So if you increase the temperature, you can see that the diffusivity also increases. So note that the x-axis of the curve is flipped. So the temperature is, so it's actually 1,000 over temperature. So you flip when you increase the temperature. So it's actually going to the right instead of going to the left instead of going to the right. So when you increase the temperature, it's going towards the origin. So that will also increase the diffusivity of each dopant or each impurity in the silicon lattice. So for example, if you look at indium or antimony, maybe antimony, the bottom one, you can see that at the highest value, diffusivity of the antimony in silicon is somewhere about 10 to the minus 11 cm squared per second, right? As a diffusivity of antimony in the silicon lattice at that temperature. So let's now look at the scale of the y, or the range of the y-axis for the right graph. So they are all interstitial diffusers like lithium, copper, iron, and gold. So if you compare the scale or the range of the diffusivity on the left graph and on the right graph, what can you see? What can you see obviously? How about the diffusivity of the dopant? How about the diffusivity of phosphorus and boron, for example, in comparison to iron at, say, so if you look at 0.7 on the on the x-axis, now let's look at 0.7. So try to compare the diffusivity of boron and phosphorus in comparison to iron. What do you get? What do you see? At 0.7 on the x-axis. Which one is higher than the other one? Which one? Anyone? BP is higher. BP is higher. BP is you mean BP is higher than iron? Naim? Adrita, you are in the wrong room, I think. Your lab session will be at 2, right? Adrita, your lab session is at 2. The brief at 2 as well. I'll see you at 2 then. Okay, Adrita, see you at 2. Okay. Okay, Naim, get back to you. Iron is higher, right? Iron is higher. Okay, you're just checking the link. That's fine. I'll see you at 2. Okay, iron is higher at 0.7. For example, if you look at 0.7 on the right, so the value is about there. So that's about 0.6 at that 10 to the minus 6, right? Something 10 to the minus 6, maybe 5, 6, 10, 6. Then on the other hand, if you look at boron, phosphorus at 0.7, for example, where is it? this line, right? So yeah, that's about 10 minus 12. Okay, so it's like 5-6 orders of magnitude higher for iron in comparison to boron or phosphorus. So we want to, in diffusion process, you want to diffuse boron and phosphorus in a controlled manner, but you don't want to diffuse all these interstitial diffusers like iron, gold, copper, and whatnot, right? You don't want them to be in the lattice in the first place. But if you have cross contamination, for example, katalah you punya chamber ada contamination, you have like all this metal, unwanted metal inside the chamber. So then you run your temperature, you run your diffusion temperature at high temperatures. So what's going to happen is instead of only diffusing the phosphorus and or the boron at that particular temperature, you will also diffuse the unwanted metals into the lattice. So this, as a result, will lead to recombination or trap centers that we discussed in 386 last time. So we've seen that these metal ions, these metals will actually be trap states, or in fact, they can also be deep trap states in the band gap. So that will suck your free carriers from the conduction process, right? So you end up not having your carriers metal contacts for the measurement, for the characterization. So this is the result that you have to bear in mind, so that you need to avoid cross contamination of your chambers in all cases, right, at all possible cost, right? So you may assume that you are actually diffusing phosphorus or boron, but then you are also diffusing unwanted metals into the lattice. And bila you check your result, then something goes haywire. So it's actually due to the metal incorporation in the lattice. So it's worth noting that the diffusivity of the unwanted metals or the interstitial diffusers are way higher than the typical dopants. Right, so diffusion coefficient. So you can see that right, D is equal to D naught exponential negative Arrhenius activation energy over KT, right, over KT. This is called Arrhenius relationship. And to be able to calculate your value of D, you know the D as given in the table here, table 4.1. So you can see various values of D naught in centimeters squared per second for different dopants. For example, boron is 10.5, aluminium 8, gallium, phosphorus 10.5, arsenic 0.32, antimony 5.6, and the corresponding activation energy for respective dopant. So you have seen in the either it's in error function or in Gaussian equation, there's a term called dt, which is the product of diffusivity times the process duration. So it's also representing a product or the driving force in the diffusion process. So the higher the value of your dt product, so the higher the impact of the diffusion process to the silicon in terms of junction depth, for example. D is proportional to temperature. We've seen on the previous graph just now, on the previous slide. Time also plays an important role to form the DT product, right? So increase either of these or both will change the diffusion parameters. So you have seen in the previous graph whether it's on error function or on a Gaussian profile. So you will change the properties of your diffuse junction, right? So at high concentration, diffusion constant becomes dependent on concentration, the value of the diffusion constant. Right. When you talk about two-step diffusion process, saya ada uploadkan video ni. Have you watched the video on Elon from UNSW on the YouTube tu? So do you see the difference between pre-dap and drive-in process? Anyone? Aniza, do you watch the video? What's the difference between the pre-dap and the drive-in? Aniza? Or anyone? Okay, what's the difference between pre-dap and drive-in? Pre-dap use infinite source. Okay, good. How about drive-in? Does it use infinite source as well? I'm trying to relate these two process steps, pre-dap and drive-in, with the constant source and the limited source diffusion process. So that's two types of diffusion process, and usually it relies in the two-step diffusion process. So normally, not necessarily, normally, we do our diffusion process in two steps. The first one is called pre-dap or pre-deposition, where you deposit your phosphorus on the surface of your silicon, or we call this as constant source diffusion step. So where you supply your phosphorus, for example, from Pockle source onto the surface of your silicon at some temperature, quite high temperature, for quite a short time, right? So this is mainly for dose control, for dose control. So dose control here means the control of Q, right? The value of Q. So then when you have already deposited your phosphorus, for example, on the surface of silicon with certain dose, you can see in the calculation later on. The next step is called drive-in, right? The second step is called drive-in. The first one is pre-dap, and the second one is drive-in. So this is done with limited source, where you use whatever you have on the surface of silicon to be driven into the silicon to form the junction, to form PN junction at certain depth, right? So in this case, you can relate these two steps diffusion process with the previous knowledge on a constant source diffusion and limited source diffusion. So in this case, the first one is going to follow the error function profile, and the second one is going to follow the Gaussian profile, right? So you can look at the description there. For drive-in, it's more of a profile control, junction depth formation, and concentration. Even though you do your profile control in the second step, you are actually building your junction as well, more or less, in the first process. That's why you need to use different equation, error function for the first pre-dap process and Gaussian profile for the second drive-in process, right? So you're already forming a shallow junction already in the first step. So the second one is to actually drive the junction to the desired level that you have designed in your device, for example. So note that the video on YouTube is for solar cell, tapi dia punya konsep dia just applicable to the IC fabrication as well, right? Konsep dia sama aja. And look at the video on the YouTube. If you fabricate your junction for solar cell, so that's how the furnace looks like. So you're going to use typically the commercial one is called triple stack furnace. You got a tiga level of tube, 3 levels of tube. So that means you're going to have your batch in the first one, your batch in the second one, and the third one running at the same time. So that will actually increase the throughput or number of wafers that can be run through the a diffusion process at one particular time. Okay, so it's pre-dep, and pre-dep is constant source and drive-in is limited source. Pre-dep is error function and drive-in is Gaussian profile. Okay. Still on two-step diffusion process. Right, a short high concentration constant source pre-dep approximate impulse dose at the surface. So this is what it means by supplying the correct dose during pre-dep process. So you are actually controlling the dose to be driven in later on. So then comes the second step, drive-in step, diffuses impurity into the lattice to form the junction, to control the junction, to control the profile of your PN junction. So in your process, if your DT product, specificity times process duration is much higher than the DT product, if the DT product for driving is much higher than the DT product for pre-dep, so you need to follow Gaussian profile, right? So let me repeat. If your DT product for driving is way higher than the DT product for the pre-dep, you need to follow Gaussian profile. On the other hand, if your DT product for driving is way lower in comparison to your DT product for pre-dep, you need to follow error function profile. Okay, so to determine the DT product, what do we do? So how do you know your DT product value? Jadi kita nak tahu driving is higher or pre-dep is higher. How do you know? Zamir, how do you know the DT product? How do we know which one is higher than the other one? What's the simplest method? Anyone? Jawapannya simple je. Saya nak tahu DT product is higher or lower. Hazika? How do you know which one is higher than the other one? Any ideas? Jenny? How do you know which one is higher? Hello? The curve? Which curve? You'll be given, right? You'll be given D and T. So senang je actually calculate je lah. So the simple word is calculation. So you can check on your D value, and then you know your process duration will be given. So you can just calculate and compare for both, right? For both pre-dep and driving steps, right? If they are given as raw data, okay? So you can calculate and compare. So then you know which equations or which profile do you need to use for your next calculation, right? Kalau you tak kira your DT product, you wouldn't know. So you need to know the DT product first. Then only you can decide, okay, for my next calculation, I need to use error function or I need to use Gaussian profile, right? So you need to know the DT product first. If you don't know, then you'll probably end up with wrong equations. Right, a solid solubility limit for dopant. So there's a limit for the amount of given impurity that can be dissolved in silicon. When you say that you want to diffuse a dopant into silicon, so there's a maximum limit, if you like, of impurity that can be dissolved in silicon. So you cannot exceed that value at a particular temperature. So at high concentrations, all of the impurities introduced in the silicon will not be electrically active. Well, this depends. It's quite a generic statement. You need to still electrically activate the dopants in the silicon. For example, if you look at this graph, the y-axis shows impurity concentration in atoms per cm cubed, and your x-axis shows the temperature increases to the right, so 900 to 1200. So you can see that when you increase your process temperature, so this process temperature actually refers to your diffusion process temperature. So if you increase your process temperature, so you can actually increase the maximum level of impurity concentration that can be incorporated into the silicon lattice. For example, if you look at boron here, oh, sorry, right, okay, boron here. So at 900 degrees C, you can only incorporate up to maybe 10 to the 20 atoms per cm cube of boron at 900. So that will be the maximum limit, or we call it solubility limit for boron at 900 in silicon. On the other hand, if you run the process at 1100, you can push the solubility limit of the boron to maybe around 1, 2, 3, maybe around 3 E20. So this one maybe 1 E20 centimeter cube per centimeter cube. So you can increase from 1 to 3, even though it's still in the region of E20 per cube. So you can actually push the maximum limit depending on the need of your semiconductor device, right? But normally, if you typical applications, even 1020 is considered really high, and you are already in the degenerate region, right? If you can recall, last time we learned in 386, we've learned about degeneracy. Degeneracy, right? You can revisit when do we start to create degeneracy in semiconductors, right? So you should know your maximum limit, especially if you want to dope your silicon at a very high doping level. So maksudnya you know what's the theoretical limit, the ceiling of the process at a certain temperature. So right, we have learned last time in our last lecture that you can determine your junction depth after your diffusion process. So sebelum ni kita belajar PN junction, let me just sketch here. For example, if you start with P silicon and then you want to fabricate IC source drain on your MOSFET, for example, left, right, you want to know the depth of your channel into the silicon. Or if you fabricate solar cell, you want to know how much emitter depth you have diffused into silicon. So to be able to determine the depth of the process after the diffusion, you can determine by looking at the curve, right? So physically on the wafer, as the process goes on, you can also watch this on the YouTube. They have uploaded about the diffusion last time. So this will be the depth, for example, D, if I can put it D, the depth of your emitter or of your channel or of your whatever, right? Channel, we call it on MOSFET. And if you look at a solar cell, we call this as the depth, right? So this will be N-type. So for example, if you want to go to 100 nano, for example, as your junction depth. So this is labeled as XJ, right? XJ or junction depth. And before if you run the experiment on diffusion to determine the junction, after the process, you can actually measure the junction physically. I'll show you how is it. But before you actually measure or before you actually design your parameters, process, temperature, process duration, and whatnot, you can come at this curve. Either it's Gaussian or it's error function profile, and you can actually sort of design your process by using this equation. So the depth on the curve will be given by the intersection point. For example, if you look at this Gaussian profile, intersection between your doping profile, the curve one, and the background doping of your silicon. So in this case, background silicon doping is here, NB, background doping. So your profile doping to dia akan start with N0 at the surface, right, where X is equals to 0, and then it will go down gradually according to the shape of the profile, either it's Gaussian or error function. But the bottom line is the junction that can be determined by the intersection between those two curve, okay, those two lines, if you like. And you can actually calculate this by using Gaussian profile or error function profile, right? So for Gaussian profile, xj is given by the first equation, 2 times square root of dt product. So dt product is important again in this case. Ln naught over nb, and naught is the surface concentration of your dopant, and nb is the background doping of the wafer, right? So it doesn't matter either you dope p-type or n-type, because your wafer is going to be the opposite side. So if you talk about error function profile, your junction depth will be given by 2 times square root of your dt product error function of n0 over nb, right? Then you can solve your junction depth. Right. When comparing the diffusion process against ion implantation in our last lecture, we have seen that diffusion profile has vertical component, some diagonal component, and also lateral component or horizontal component. So you can look at this sketch on the right. Inside, you have mask on the wafer, so you want to diffuse certain areas and you want to block some other areas. So if you translate that into the left sketch or left illustration, so here is your diffusion mask where you actually block the dopant from coming into the silicon for doping, and this is the areas that you expose for the dopants to come in, and the diffusion mask is the areas that you want to block dopants from coming in. But due to the nature of the diffusion process, which has lateral component as well, so you're going to see your junction forming your dopant, if you like, diffuses vertically into silicon, and you also have some diagonal component at some degrees from your normal angle, and also you have some lateral component under the mask. So this is how you're going to end up on your device. So if you talk about low technology node IC, so when your well, the size of the gate perhaps is below 20 nano or so, when your your MOSFET is really small, or either it's MOSFET or FinFET or GA-FET, so the control of the diffusion profile will become very critical, right? Because if you have no control or less control over the lateral component of the diffusion profile, you can actually short your device, right? So this is how it looks like the deeper it goes into the silicon. So the first one is for error function, the second one is for Gaussian profile. Right, typically the concentration profile of your dopant will be like this, but it'll be more abrupt. It'll be more abrupt at high doping concentration, right? More abrupt means if your gradient tu akan lebih tinggi lah. If you go for higher concentration of your dopant, either it's arsenic or boron or phosphorus, whatever. You will also see later on when you finish your diffusion process, you'll need to do some measurement in order to characterize what you get on the wafer, right? What you get on the wafer and what sort of profile do you obtain. So for phosphorus diffusion profile, you normally see some kind of kink. Kink here means Macam dia ada kat sini king. This is king. Dia turun tapi dia tak turun macam you look profile like that. Or this function. So it doesn't go down that way. So dia tak follow a nice curvature lah if you like. So instead dia turun tu dia ada macam dia ada corner sikit ah. This corner is what we call kink. This is unique to certain dopants. So for this particular case, it's due to the phosphorus profile, right? So you normally see a kink, right? So which makes it harder to predict what are you going to get in the actual device. So you will still need to do some profile measurement characterization in order to understand what sort of profile you get at a certain depth, right? So for example, if you see this profile, the kink for this particular case is happening for 30 minutes diffusion process at about maybe 0.6 micron. Right, so you need to know where do you get the kink, at which process, which temperature, at which process duration, and then at which depth into the silicon as well, right? Especially kalau you ada various kind of devices and various designs and various stacks and various dimension, you will need to know this exactly on the behavior of the profile, so that you get what you as what you've designed in the design level, at the design level, right? Okay, so we have learned this one last time. Resistivity versus doping. So kita dah belajar waktu 386 when we learn about carrier transport, I think, carrier transport phenomena. So we've learned about resistivity versus doping. So I've explained last time in the class that kalau you ambil silicon wafer from the cassette. So let me show you the cassette. You've not seen, maybe pick up the cassette. Okay, this is how it looks like. Ni untuk lab scale silicon wafer. So this one is 2-inch. Well, I hope you can see the label there. So it's from SWI. So it's for 2-inch silicon wafer in here, P100 that I use here. Diameter 2-inch, 50.8 mm. In the other unit, thickness is about 275 micron. Resistivity, it will state here the resistivity as well. Resistivity in this case is 1 to 10 ohm cm. 1 to 10 ohm cm as what is stated on your y-axis. So maknanya dalam batch ni, dia guarantee the resistivity variation between wafer 1 and wafer 25, altogether 25 wafers. So when you pick one randomly, so the resistivity of the wafer that you have in the pack is somewhere between 1 to 10 ohm cm. So let's look at this curve and let's look at the doping concentration variation that we have. Right, so it's p-type. So you tell me what's the value now. So what is the doping concentration for my 1 ohm cm p-type wafer? Right, someone tell me. So it's 1 ohm cm there. So what's the doping level that I have in this pack? Someone look at the curve and tell me. P-type. Ada dua tu. P-type is on the right hand side. N-type is on the left hand side. So berapa value doping concentration yang ada dekat, right, 1 ohm cm, that's about 116. Yep, that's about 116. Great, good. Okay, so now if I pick another wafer and then the resistivity is around 10 ohm cm, now you tell me what's the value of p-type concentration there. So what's the value now? Berapa doping concentration? Curve yang sama. Anyone? It's straightforward, kan? You just have to read the graph and that's it. There's no analysis required. Just read the graph and you tell me. So what's the value there? P-type 10 ohm cm. Anyone? Come on. Yep, 1015, right? Good. So it's 1015. So that's about 1E15, right? 1015. So if I pick this randomly, so maksudnya saya punya doping concentration tu will vary from 1E15 to 1E16. So that means it's quite wide. It's quite broad in terms of the doping concentration. If my project works on the doping concentration, so that means I might have some variation in the sample already before working on the device level. So you have to be careful then. Maksudnya, tapi usually untuk beli untuk lab scale punya wafer ni, if I buy for 1 to 10, it's going to be cheaper than if I buy the very same pack, but the resistivity control is 1 to 3 ohm cm, right? So the tighter the resistivity control in the pack, the more expensive the pack becomes, right? So fair enough, 1 to 10 is fine in my case, but in some other applications, you might need to control between 1 to 2 ohm cm only, or else your device will show some variations. So for example, if you look at, for example, you fabricate MOSFET on this silicon wafer, and then you don't know the variation, so maksudnya you punya body tu, you ada gate, aux, source, drain, and the body, right? So your body already have different resistivity or different concentration to begin with. So maksudnya kalau you buat something on the source or on the gate aux or on the gate or on the drain, so you might see something, you might see some different that is not due to your processing, but rather is due to your concentration of your wafer, of your original wafer. So you have to be very careful when you design an experiment, and you have to make sure that you have a very tight control of your starting wafers in order to make sure that your final results are as desired, right? So you can use this equation on the right. We've discussed this one last time when we talk about carrier transport phenomena. So resistivity is connected to mobility and also conductivity. Resistivity is reciprocal of conductivity, 1 over conductivity, or sigma, and also equals to Q, electronic charge, times mu, mobility for electron, mobility for hole, times N times P, and invert that, right? So N-type dengan P-type pun kat sini sama lah. You've learned about MD, you've learned about NA last time. You can do that by majority carrier and minority carrier calculation. So now you know how to use the curve already. When we finish the diffusion process, so tadi kita dah discuss on the diffusion process. So now we have done with the process. So what can we do? So we need to measure, or we need to characterize your silicon wafers, of course. We need to characterize your doping profiles. We need to know your anode. We need to know how your doping profile looks like. We need to know what's your junction depth. And we need to recheck on whether your outcomes from the process match with whatever that you have targeted. So these can be characterized by using a couple of different characterizations. The first one is called ECV, electrochemical voltage potential, ECV profile. So ECV, they can plot, okay, you can look at the title up here, measurement, doping level, and junction depth. So ECV can tell you the doping level and the junction depth. So it can actually plot the profile of your dopant, either boron or phosphorus or some other dopants. SIMS is secondary ion mass spectrometer. SIMS, secondary ion mass spectrometer. It can also measure both. So normally if you want to characterize the profile of your junction, of your dopant, for example, you can either use ECV or SIMS, right? If you don't have SIMS, you can go for ECV. If you have ECV, you don't have to use SIMS. So either one is fine. So because they can measure both. On the other hand, if you can use another characterization, it's called Hall effect. Kita dah belajar Hall effect in this course, and if in fact in the previous course as well, 386. But it can only measure your doping level, but it couldn't show you the profile, right? Another one that you can see on the video that I've uploaded from UNSW, you can also use 4-point probe, the simplest method. So 4-point probe, dia boleh bagi tahu you the shear resistance, the resistivity, then from the shear resistance and resistivity of your surface of the silicon, you can come back this curve and then you can predict what is the carrier concentration inside the profile, inside the dopant profile, right? But it's not accurate, but it's the simplest one, right? If you want to know the exact profile, how does it look like, the junction depth and everything, you have to go for ECV or SIMS, right? ECV and SIMS are destructive in nature. So that means you have to sacrifice a sample in order to measurement, in order to characterize your dopant profile. You cannot recover basically. So what it will do, you can explore yourself. It will actually etch your surface of the silicon. It will remove the surface by etching process. Then during the etching process, it will do the measurement to track, to measure the number of atoms per cm cube of your phosphorus or of your boron. Then it will plot the profile accordingly, right? If you talk about SIMS, it uses ions in order to etch the surface and then does the measurement as well, right? So I think I'll just stop here. We have a few more things on the diffusion, right? So today is what, Tuesday? So tomorrow I'll continue on the shear resistance and I'll try to finish diffusion process, and we'll go through this calculation as well. I want you to try this one first and then call one of you perhaps to show me your answers for each of the question, right? Okay, any questions for now? Ada soalan for today's class? Anything? Okay. All right then. Okay, then I'll see you tomorrow. Inshallah. Bye bye. Take care. Assalamualaikum.